Today what we're looking at is a scheme interpreter written in Scheme. So just first off, why isn't that a stupid thing to do? Because you can't run it unless you already have a scheme interpreter. And it's going to run slower than the one you already have, so what's the point? And the point, of course, is pedagogic. It's for you to learn what an interpreter looks like. But also it means later in the semester we can play with variant versions of Scheme. We can say, what if we take Scheme and add this feature to it, or change the way it does that? And we'll see some of that later on in the semester. So it lets you do that. It also makes a point. I'll talk more about this when we get to Chapter 4, where the book starts doing interpreters. It makes a point about universality of a programmable computer, that we can write one computer program, namely the interpreter, that can do any computation by taking as data a formal description of the algorithm that you want to use. So the Scheme interpreter takes a Scheme program as part of its input data, and it turns that into whatever result you want. And that's really an amazing thing to be able to do, right? Universal programs. You guys all grew up with this. I just barely grew up with it. I was born just about the time they were building computers that could do that for the first time. A little later. I missed it by a decade, I guess. All right. Up on the screen is the one screenful version of a Scheme interpreter in Scheme. And we're going to start by going through this. It should really not scare away anybody, I think, because it's very simple and you can see all of it. So up at the top is the read eval print loop. It's just like what you remember from the calculator program. It reads an expression, it calls eval on that expression, and then it prints the result. Okay? And then it loops. So read eval print loop. And then we have eval and apply, the same as the big pieces of the calculator program, except because this is Scheme instead of calculator language, it's more complicated. We have things like variables. So in Scheme, there are 4 kinds of expressions. And you can sort of divide them up into 2 groups like this. So here's expressions. And there are atomic expressions, and there are lists. Atomic means you don't divide it up further into pieces. You just look at it as one thing. So now there's 2 kinds of each of those. The atomic expressions come in self-evaluating. This we saw before in the calculator program, where it was the numbers that were self-evaluating. In Scheme, there are a few other self-evaluating things, like number sign T and number sign F are self-evaluating. Strings in double quotation marks are self-evaluating. There are a few other things that we're not really getting into. So they're self-evaluating, atomic expressions, and then the thing that's new is that there are symbols, which are the names of variables. And those are not self-evaluating. The value of a variable is, whatever its stored value is. But it is atomic. When we see a variable, we're sort of at a base case of the recursion in eval. So we have the variable as just a thing to look up and find out what its value is. And then there are lists. And those come in 2 kinds also. And they are the most usual kind. There's a procedure call, procedure invocation. Those mean the same thing. So usually when you see stuff in parentheses, it's procedure, argument, 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 and we're calling that procedure with those arguments. And the other thing that's in parentheses is what? Special forms. And what's special about special forms is that they don't follow the rule of applicative order. Namely, we don't have to evaluate all the sub-expressions first. And each special form has its own rules for what it evaluates and when and under what circumstances.